Hi everyone, and welcome to lesson 20.2. Today's lesson starts on page 286 in your Springboard book, and you are definitely going to want a pencil and a calculator handy. So today's lesson starts by kind of reviewing what we talked about yesterday with Pythagorean Theorem. And notice we have this right triangle shaped kite. So we have a right angle here at angle R. So we know by yesterday, what we talked about was that our two legs, 40 squared or 40 and 42, those two values squared and added together are going to equal our hypotenuse squared, right? Hypotenuse is always the longest side and across from the right angle. So we talked about if this is happening in a right triangle, and then that the Pythagorean theorem would hold true. So if we think about our if-then statement, we have a hypotenuse here, and then we have this very, very long conclusion about Pythagorean theorem, right? And so we know we use Pythagorean theorem when we have the right triangle. Well, what if we wrote the converse of that? What if we flip-flopped the order? What if it was now, if the square of the longest side, that second piece, that if the Pythagorean theorem holds true, then it is a right triangle, right? If we put that second. That's also going to hold true because if we know that this is satisfied, that the left-hand side equals the right-hand side, Pythagorean theorem is working. So that's known as the converse of the Pythagorean theorem, that if this is true, we know our triangle has to be right if that's going to work out. Okay. Also reviewing from yesterday, or excuse me, before we review from yesterday anything more, let's test that out again. In checking this, we see that this does in fact equal 1600 plus 1764 does equal 364 because these check out. So we know that the converse held true, that this is in fact a right triangle. Okay, so that's what they wanted us to do for part C, was just check that that was true. Now something else that we talked about yesterday was the idea of a Pythagorean triple. And that's when we have values, for instance, we talked about yesterday, 3, 4, and 5. These are a Pythagorean triple because 3 squared plus 4 squared equaled 5 squared. Our Pythagorean triples are nice positive whole numbers that satisfy Pythagorean theorem. Well, what this bottom piece talks about is that your Pythagorean triples, such as 3, 4, 5, if you multiply all of those lengths by the same value, let's say 2. Let's say, so now we have 6, 8, and 10. This is also going to be a Pythagorean triple. And again, we can test this out. So 6 squared plus 8 squared, does that equal 10 squared? Well, yes, 36 plus 64 does in fact equal 100. So that worked out too. And so that means if we multiply 3, 4, 5 by 3, so it was 9, 12, and 15, it would also work out in Pythagorean theorem. That's just another little side note here based on what we did yesterday. Now, moving on from there and continuing on with the converse idea, okay, there are other triangles out there besides our Pythagorean triple or our right triangles, even if they're not triples. There are other kinds of triangles, right? We have acute triangles and we have obtuse triangles, right? There's other kinds. So we want to see, using the converse of the Pythagorean theorem, is there a pattern that is holding true so we can identify if something is right, acute, or obtuse. So first and foremost, we need to decide, is something even a triangle? And we touched upon this a little bit yesterday. But what we discovered yesterday was that there's a special pattern between our two smallest sides and the biggest side of any triangle, acute, right, obtuse, whatnot. And what we're noticing here is if we drag, or if we adjust these side lengths, as long as A and B are greater than C, the longest side in our triangle, they're going to create a triangle. It's when we make these too small. So for instance, if we have one that is 3 and 3, it's unable to make a triangle or anything smaller than 3. So notice if we add these two together, if this isn't happening, if this isn't satisfying that it's bigger than 3 when we just add A and B together, it's not going to be a triangle. Another way to look at that, like this one, if we have these side lengths, we can adjust them. Notice A and B together are bigger than, A and B. Here, we'll do it so that C is A is our biggest side right now. But these two added together are, in fact, greater than our biggest side. So we were able to make a triangle because 7 plus 9 is bigger than 12. But if we adjust this, let's say to be 6 and 7, let's say 5 and 7, where it's equal to 12, 5 plus 7 is equal to 12. These are going to be too short to ever actually touch each other and form a full triangle. Or if it's equal, let's say these were both 6. Again, they have to be greater than that third side or they're never going to reach each other. So the minute we make this so that 7 plus 6 is 13, we're able to adjust these again so that they do create a triangle again. Okay, so that is the first piece of these when we're testing them out. We need to first check, is it a triangle? And the way we do that is we take our two smallest sides without squaring it, and we need to make sure that it's bigger than the third side. Okay. Now, part B is using that converse of our Pythagorean theorem and checking out then what happens. We know that if the a squared plus b squared equals c squared, it's going to be a right triangle. That's what we talked about is, Pythagorean theorem and its converse. But again, we have other kinds of triangles. We have acute triangles and we have obtuse triangles. So if we make this into an acute triangle where all the angles are less than 90 degrees, what we see with the sides is that if we take a squared plus b squared, that value is going to be bigger than c squared. And that's happening for all of these triangles that are acute, where these angles are less than 90 degrees. A squared plus b squared is bigger than c squared. But if we change this so that it's an obtuse triangle, so we have one angle that's bigger than 90 degrees, notice this flip-flops. A squared plus b squared is less than c squared. Okay, and that's happening for all of these, no matter, as long as the triangle is bigger than 90-degree angle, that's happening where c squared is the biggest. Okay, acute, then it flip-flopped back the other way. So that is an important piece then, is to check then what happens to a squared plus b squared. How does it compare to c squared? Okay, what's going on here? Because what we see down here is if a squared plus b squared is equal to c squared, it's a right triangle. If a squared plus b squared is greater than c squared, it's an acute triangle. And if a squared plus b squared is less than c squared, it's obtuse. Okay. Very important that you have this piece in your notes because it's going to help us decide about our triangles. Okay. So again, each time you first want to decide, is it even a triangle? And then we're looking at what happens when we square the sides of the triangles and add the two smallest together. Okay. So for instance, if we look here, first off, let's double check. Is this even a triangle? So are the two smaller sides, which we're going to call A and B, are 12 plus 34, is that bigger than 37? The answer is yes. So it is, in fact, a triangle. So we can proceed now and look at this other part. If it's not even a triangle, don't waste your time even doing the next part. You would just say not a triangle, but this one is a triangle. So as we move on then, we want to check out, how does 12 squared plus 34 squared, how does that compare to 37 squared? Well, let's see. 12 squared plus 34 squared is 1,300, but 37 squared is 1,369. So 1300 is less than 1369. So when it is less than that, we know it's going to be obtuse. So the answer here is this is an obtuse triangle. Now in the next one, if we're going to test out what is this a triangle, notice all of these have a denominator of 7. So really we just need to test out the numerators here. How does 6 plus 8 compare to 10? Is it greater than 10? Oops. And the answer is yes, 6 plus 8 is greater than 10, so this is a triangle. So now we can move on to part 2, where we're going to test out 6/7 squared plus 8/7 squared. How does that compare to 10/7 squared? So if we look at this one, we're going to use parentheses, 6 divided by 7, and then squared, plus, again, parentheses, so we get everything taken care of, 8 divided by 7 squared. Notice we get this answer here, or if we make it into a fraction, 104/49. And now we want to see how does this compare to 10/7 squared. Again, make sure you have it in parentheses. Oops. We insert a 0 here. 10/7 squared. Notice it's that same value of 100. Okay. So these are equal to each other. We know when they are equal to each other, it's a right triangle, right? These ended up being equal, so this one is a right triangle. Now a shortcut for any of them that are fractions also, if they all have the same denominator, again, just test out 6, 8, and 10, and you would see that those are equal. So when they all have the same denominator, you can kind of shortcut that as well. Okay, last example. First of all, again, check, is this a triangle even? Okay, is 20 plus the square root of 42 bigger than 21? Well, you might not know what the square root of 42 is, so 20 plus the square root of 42, that's bigger than 20, so that works out to be a triangle. So we can proceed now and say, okay, 20 squared plus the square root of 42 squared, how does that compare to 21 squared? Okay, well, 20 squared plus the square root of 42 squared, which we know the squares are going to cancel out, but still we see here is 442. And then 21 squared, 441. So because a squared plus b squared was bigger than c squared, we know that this is going to be an acute triangle. Okay. Couple more examples. If we look here, we have this customer who has a triangle with these inches. What do we notice? Is this even a triangle? Classify it. Well, 27 plus 34 is in fact bigger than 45, so it is a triangle. And then when we test out 27 squared plus 34 squared, how does that compare to 45 squared? Well, what you should get on this is that 27 squared plus 34 squared, it's not 3 squared, 34 squared is 1885. 45 squared, though, is 2025. So because the c squared was bigger, this becomes an obtuse triangle. Okay. Thanks everyone for watching. We will work more with this in class. Remember, make sure you always check, is it a triangle first, and then look at what happens to a squared plus b squared compared to c squared. When it's equal, it's right. A squared plus b squared being greater is acute. A squared plus b squared being less than c squared is obtuse. Thanks for watching.